Hi everyone, welcome to the Great Beyond. Let's talk about sound and waves. My name is Mr. G, and today in the Great Beyond, we're going to learn more about sound wave properties. First, let's take a quick look at something. So, I've got in here a ping pong ball, and I want to know what's going to happen when I shake it. What do you think is going to happen to the ping pong ball when I give this a great big shake? Yeah, probably is going to bounce around quite a bit. Well, what did you see? Yeah, I saw it too. It was hitting almost every single wall. Either it was the top of this or it's one of the sides here, but the ball just ricocheted off every surface possible. Now, the importance of this has to do with what waves are. That's why I did this quick demonstration with you. Sound is similar to that bouncy ball. That ball hits off of other objects and then bounces in another direction. How many of you have ever been somewhere where you can yell out loud and it somewhat echoes? An echo is when those sound waves are bouncing off and coming right back to you, or it's continuing to carry through whatever room you're in. There's quite a few cool phenomena we will talk about in just a second. But first, let's break down what a sound wave is. A sound wave is what we like to call a longitudinal wave. A longitudinal wave is a very high science term to say that the wave travels in the same direction as the medium it's moving through. Now, there's a lot of science terms in there. Let's break that down. So, we know what a wave is. A wave is a movement of particles, right? So, this ping pong ball is an example of an air particle moving around. A medium is a substance or material that can carry a wave. And we know what a wave is. In water, we have the ocean. The ocean is an example of waves traveling in a medium because the water is the medium the waves are moving through. In the Tupperware example, we had a ping pong ball moving through air. The air was the medium. In a sound wave, similar to a pebble being dropped in a calm river, the waves move in the same direction as the medium. So when a sound wave is moving, it moves in the same direction as the air particles. They're being pushed, kind of like the way jellyfish move through the ocean. How many different examples of sound waves or waves in general can you come up with? Great, so let's now break down what the individual parts of a wave are. A wave has amplitude, frequency, and what else? Wavelength. Amplitude has to do with how tall the wave is. And sound waves, we like to think of that as how loud or how quiet the sound is. The larger the wave, the higher the amplitude, the louder that object probably is when it's making noise. The shorter, the smaller it is, means it's a little bit quieter. Wavelength has to do with how many times the wave moves through a medium in a certain amount of time. That's frequency. When we measure frequency, we're measuring the wavelength in a specific amount of time. Let's take a look at a couple of images to maybe help figure this out a little bit more. So let's take a look at this graphic here. We have wavelength, amplitude, and frequency. Wavelength, as a reminder, is the amount of time it takes for sound to return to its identical starting point. I'll go over that in just a second. Amplitude is the maximum height of one half of the wave, and frequency is the number of times per second a sound wave repeats itself. So if we take a look at this graphic where I zoomed in on the sound file, you can see that I have two vertical lines going up and down. Those are marking the crests, the amplitude of the waves, and that arrow that's pointing in between is showing wavelength. We're measuring from one starting point all the way back to that same point again, and that is what wavelength is. Amplitude is the height of that crest, how tall that crest is. Now if we want to be on the flip side, the part that dips below that black line, then we're going to call that the trough. So let's recap where we are. We learned about waves. We learned that there's a wave called a longitudinal wave. A longitudinal wave is one that travels in the same direction as the medium it is moving through. And we learned that a medium is a substance or material that a wave travels through. And we have mediums where it is air, a gaseous state of matter, or we have water, a liquid state of matter, and waves can travel through both. We also have other kinds of waves like radio waves, light waves, and we have waves of like the sunlight coming in. We have color, UV radiation, X-ray waves. There's a lot of different kinds of waves that exist in our world today. We specifically were talking about sound waves and how sound travels through the air to our ears. We have these things called eardrums that pick up on that vibration and turn that vibration into information our brain can understand. This is sound. Sound has a wavelength, an amplitude, and a frequency. The more frequent a wave is occurring, the faster it's moving. As it moves out from its source, the gaps between those waves may be slower or faster. So if we look at a droplet of water, we can recall that the water moves out from the center in all directions. There's a bunch of different ways we can discover sound. One really neat trick you can do is take a portable Bluetooth speaker, put it in a plastic Tupperware, put some sand on top or some rice uncooked, or even you can make oobleck, which is cornstarch and water, and you can watch how the base of your portable speaker affects the particles on top of the speaker. Now, these are all experiments you can do at home. You can look up YouTube videos. They're all really cool. But you know what? They are not in the great beyond with me, Mr. G. Thank you guys for tuning in, and I can't wait for the next episode. See you guys later. Bye-bye.